and is interested broadly in theoretical astrophysics. He is a Goldwater Scholar and U.S. Presidential Scholar. He is co-president of Harvard Students for the Exploration and Development of Space and former senior U.S. editor of the Harvard Political Review. His research advisor is Professor Abraham Loeb.
Amir Siraj, welcome back to the program.
Thanks for having me again, John.
Now, Amir, in a recent paper, and we talked a little about this before, but to dig deeper into it, in a recent paper, you have reported finding two candidate interstellar objects, meteorites of interstellar origin that could be sitting on the surface of the Earth right now, opening the way for studying such materials right here from home. But beyond that, they appear to be materially weird. In other words, they are harder than they should be compared to normal meteorite falls in our solar system of an iron nickel nature. So that these might be and might represent something really weird. Tell us about the option that these might be materials forged in a supernova.
Absolutely. So we have two objects that we're interested in. One, the first one, which we call the IM-1, struck off the coast of Papua New Guinea in January of 2014. And the second one, which we call IM-2, Interstellar Meteor 2, struck off the coast of Portugal in March of 2017. Now, IM-1 is the object which we received confirmation of its orbit from the Department of Defense, basically confirming that the sensors were correct in detecting a very high speed and unusual direction, meaning that this object was from outside of the solar system. Now, IM-2 looks somewhat similar to IM-1 in terms of its dynamics. It came in very fast and at an unusual direction. But of course, we don't know the uncertainties on it and haven't received any official word or memo from the DoD or elsewhere yet. So IM-1 is confirmed, IM-2 is still awaiting confirmation. The Department of Defense, though, also released light curves for these objects. And from the light curves, we can figure out, and also the altitudes at which they burned up, we can figure out what kind of ram pressure that they were experiencing in the atmosphere as they were moving through it. And this ram pressure results from friction with the air and basically goes as the density of air times the square of the relative velocity between the air and the object. And we computed the ram pressure at breakup, which is a measure of material strength, for all 273 odd objects in the CNEO's catalog, which is the US government's catalog of fireballs that it observed using its satellites. And what we found is that IM-1 is the strongest in the entire catalog, and IM-2 is the third strongest in the entire catalog. So this is very interesting and unusual. IM-2 had a material strength of about 75 megapascals, which is consistent with a typical iron meteor tends to break up at about 50 megapascals. So this is fairly consistent with that. However, IM-1, and by the way, iron meteors are very unusual. Only 5% of observed meteor falls are iron. IM-1, on the other hand, exhibited a material strength of about 194 megapascals. And so this is above, definitively above the typical iron meteor strength. And this doesn't mean that it's not made of iron, but the structure might be different, and the way it's put together might be different. Of course, it could also be a mixture of other metals. But one possibility is that we see clumps of material spewing out from supernovae, and these clumps are often rich in iron. And one can imagine supernovae spew out extraordinary amount of mass like this. And one can imagine fragmentation on smaller scales within these so-called supernova bullets, leading to small microwave or fridge-sized objects like IM-1 and IM-2 being formed from the debris, from the aftermath of a supernova. Of course, this is just one speculative possibility. You know, I was just thinking the other day, it could also result from some chaotic collisions in early planetary system formation. You know, maybe you collide two cores of giant planets, or you somehow fragment the core of a giant planet. But basically, we need some pretty extreme astrophysical events to produce these kinds of high-strength objects. And this paper that I wrote with Avi, that was recently published in the Astrophysical Journal Letters, argued that if indeed IM-2 is confirmed, it's very unlikely that IM-1 and IM-2 interstellar meteors have the same origin as solar system meteors that originate from within the solar system, because the strength is so unusual. The chance of picking the first and third strongest out of 273, you can do it two different ways. You could do a Gaussian way, or you can just say picking it out of a hat. But the point is that if IM2 is confirmed, there's between a 1 in 10,000 chance and a 1 in a million chance that these two populations can be reconciled. And so this points to maybe something exotic and exciting happening that we can understand better by actually getting samples of these meteorites that may be left on the ocean floor, and by trying to find more examples of interstellar meteors.
Now, within our own collections of meteorites, and I know that there are certain catalogs, but I don't know what kind of data those catalogs have. For example, the British Museum once did a fairly extensive catalog of known meteorite falls. Is the data available for us to check our collections and see if material in this number is already?
Definitely. To my knowledge, I don't think there's a centralized data on meteorite composition as there is on meteor dynamics. But once we are able to get our hands on a piece of IM-1 or of IM-2, then I think we can go back to all of the meteorite collections and see if we can find something of similar composition. And that will allow us to both calibrate the abundance of interstellar meteors and of these objects, and provide us a window into a much more broader window into where they come from. Basically, the yield strength that we see in the atmosphere when the object breaks up is different from the compressive strength or tensile strength of a resulting meteorite. And the reason is pretty straightforward. If you could have broken up that meteorite in the atmosphere, that little rock that you found on the bottom of the ocean or on the ground, it wouldn't have broken up. Now, the larger object did break up, and so it's a matter of, let's say, a meter scale fireball might have a yield strength of, let's say, 2 or 3 megapascals, some stony, indicating that it's a stony meteor, but the resultant meteorites might exhibit compressive or tensile strengths of 20 or 30 megapascals. So there's not as straightforward of a way to convert those two. They tend to be roughly an order of magnitude different. And so the route that I would advocate is twofold. One is that we find a piece of IM-1 and or IM-2, and then we look for similar objects in our catalogs. And then secondly, it's worth constantly searching through the catalog of known meteorites for unusual isotopic abundances. Now, this has been done, but when it's done comprehensively and it's combined with samples that we find from confirmed interstellar meteors, it'll really shed light into where these are coming from.
Thanks to centuries of technology and a little luck, a discovery like this meteorite could tell us more about the world outside the one we know. And as it just so happens, today's sponsor, Masterworks, has unlocked the potential of another mysterious phenomenon, paying out tens of millions of dollars last year by transforming artwork
From a fascinating conversation starter to an addition to your portfolio, Masterworks is an award-winning fintech startup based in New York City's financial district that grants everyday investors like you and I the opportunity to invest in shares of high-end contemporary art. Think of names like Picasso, Basquiat, Banksy, names that generate millions of dollars at auction. With Masterworks, you can invest in art like this for thousands, not millions, and potentially reap the benefits of their appreciation in value. Like their last 3 exits, which delivered net returns of plus 10%, 13%, and even 35% to their investors. Quite a few of which happen to be our subscribers. Over 617,000 people have signed up so far, and offerings have sold out within minutes. But our subscribers can claim a free, no-obligation account at the link in the description.
One thing about the meteorite world is that the most poorly studied type are the irons, because you just don't have the sort of shock data and things like that that you can study with stoning meteorites. So you just essentially have a piece of iron. However, there's a huge variation in how these things crystallize and form what's known as a Wittgenstein pattern. And sometimes these crystalline boundaries between iron and nickel alloys can be very wide-ranging, to the point where you can end up with giant crystals, and I believe they're known as ataxites. So you can actually have perhaps a different variation within known iron meteorites as far as hardness goes, it seems to me. Do you think that that would be a fruitful place to search to try to see if there actually are meteorites this hard in our collections?
For sure. Yeah. Studying how the structure of an iron meteorite or iron nickel meteorite maps onto tensile or compressive strength would be crucial for understanding how that relationship scales to these meteors blowing up in the atmosphere, and then for contextualizing what we end up finding from IM1 or IM2. So it's absolutely a worthwhile research route.
Now, the idea of supernova material, a supernova bullet, it would seem to me that that would produce something isotopically so bizarre compared to the solar system that it would be unmistakable. In other words, it's an environment that is completely different from what our protoplanetary disk would have exhibited when the solar system formed. So this would really represent truly exotic material for us, something we've never seen before that might give us a probe into the deep chemistry, perhaps, and deep nucleosynthesis that goes on during a supernova, right? So this could be a huge area of study if it turns out that these things actually are from a supernova origin, right?
Exactly. And one of the ways that we might find that out is, obviously, it is much harder to study iron meteorites, in particular ones that have experienced ablation. And because this is a relatively small fireball, this was 0.1, so basically 100 tons of TNT in terms of energy. So, say a meter in size. Most of the products, so we wrote a paper with Amory, Tillinghast, Rabi, and Avi on the expected fragment distribution, and there is a lot of mass that's going to be ablated. However, even in those ablation spherules, we can study chromium isotopes, for example, and those should exhibit very wide variations relative to those we find in the solar system. And so it will be very clear if what we find is from the solar system or not, and in particular if it's from a supernova. And the hope is that if we find something like this could provide a new window into studying the cosmos. And chemists and geologists, people who know much more about studying rocks than Avi and I, astrophysicists, will be able to contribute a lot.
Fragment size. Now, you mentioned ablation, bits and pieces, droplets. It would seem to me that, though, that would be the type that has the most widest distribution, as opposed to if you just happen to come across some kind of main mass or a big 10-kilogram chunk or something like that. But over a large area of ocean where you have to surge, it seems to me that sort of ablative material would be very widespread. much more so than main masses would be. And I think there's precedent for that with the NOAA's recovery of meteorite materials. A very small amount of material that they managed to recover from meteorite fall using similar methods. And it looked really like that it was ablative material. So is that what you expect to find, or do you expect to actually find big chunks?
Yeah, we do expect that most of the things that we will find will be relatively small. I think the number that we found from the simulation in where we ran are between 14 and 36% of fragments from IM-1 being expected to survive ablation with a mass greater than 10 to the minus 3 grams. So these are pretty small masses. Now, the largest ones, I think we expect tens of fragments to survive with a post-ablation mass of greater than 10 grams. But those are really the largest that we expect from our simulation, from our model. And because because this exploded high up in the atmosphere and we are doing our best to survey that area, we're obviously not going to find every little bit of IM-1. However, I should mention that if there is, these are all based on assumptions about iron and about the composition of the meteor, and we even tried putting in something like steel, but the composition and the structure of the meteor is unknown. So, I mean, of course, there could be a larger fragment because we only modeled what we knew, and in that case, the larger fragment would be found basically continuing along the meteor's trajectory and then hitting the ocean surface. The smallest fragments sort of rain down wherever the explosion happens, and the larger ones tend to continue along the velocity vector. So what you get is a line of fragments, and the closer you are to the explosion site, underneath the explosion site rather, those are where the small mass fragments rain down. And then the further you are away, along the line on the ocean that's the velocity vector, those are where you'll find larger mass objects. And so once we get our hands on, let's say, 3 gram little bits of material, then we can simply travel along these active meteor and check if there are larger fragments.
Now, another recent paper involves the mysterious object Oumuamua and like objects, presuming the frequency of populations, and catching up with them and being able to explore them. What's that look like? I mean, what are the dynamics of actually going up and catching up with an object on a hyperbolic trajectory?
So it's really hard for a number of reasons. It's much harder than going after an object that orbits the sun. Firstly, because when you're going after an object that orbits the sun, you have a lot of time. You have a lot of time to plan the mission, to know exactly what object you're going to go after, and to calculate the lowest energy, intercept trajectory, etc. And also, let's say you miss it on the first try. Well, that's okay, you can always try again. Now, none of that is the case with an interstellar object. These things, we only know that they exist, let's say, a order of months, not even shorter months before we. And so, this mission is going to have to be built and ready to launch before we even know what object it's going to go to. And then secondly, because of the combination of the fact that we only have one shot for an object of interest, and because it is on a hyperbolic orbit, which means that it has more energy in the first place, that's why it's starting down to a star, the relative speed, and thus the delta V budget, has to be much higher than for a conventional mission to a solar system body. And so that's what makes going to an interstellar object very different. And so, as director of interstellar object studies for the Galileo project, this is something that we really wanted to, in our branch of the project, understand from a physical perspective, how hard is it, and also given the detection capabilities that we're going to have from LSST on the Vera Rubin Observatory, how soon will we know? And what speed will these objects be traveling? What kind of delta V do we need? What's a chance that we can actually find one of these objects? What size object should we go after? And so with a team of about 10 people across the country and some even international, we studied this problem and we put together a paper that sort of outlines the physical realities of what this mission.
It seems to me that it would be sort of hard to design an instrument package for it that was so general that you could use it on any object that comes through. So do you anticipate challenges there as to coming up with a generalized instrument package to explore these objects?
Right. We're not instrumentalists, and so that's why we didn't try to pick the instruments that should go in this payload. However, we did study the kinds of sort of considerations from a physical standpoint that these instruments would have to contend with, and it's mainly the fact that you don't have much time to be able to make these measurements. You know, the flyby timescale at closest approach is very short, and additionally, for a lot of the time, I mean, even at close approach, there is a significant limitation in terms of the pixel size, even in the diffraction limited regime. And so we need a very, I mean, the larger the aperture, the better. And that has to contend with the mass, because the more massive the payload, the higher the delta V. And it also has to contend with maneuverability, because this will have to be ready to be in place at that very short close approach window. And so these are the kinds of things we look at: the diffraction limited regime, the flux limited regime, the encounter time scale, and how all of these scale with the detection rate, object size, and delta V.
Now, given the weirdness of our detection of interstellar objects in space, one was very strange indeed, and it was the first one we spotted in space. And the other was a perfectly normal comet. So it seems that we're going to have to pick and choose, but doesn't that seem to suggest, and I know this is another that doesn't this suggest that there is a large population of Moon-like objects out there, and that once that LSST telescope turns on, we're going to see a lot of them very often, and if we don't, that makes it even stranger, doesn't it?
That's exactly right. So in this paper, our rationale was, if we wanted to spend $1 billion on a space mission to have one shot of going after an object, we would probably want this to be a very unusual looking one, something like a Oumuamua that doesn't look like a comet from our solar system. And there was only one Oumuamua. So that's a tricky situation to be in, and Poisson statistics actually give a very wide distribution of possible background densities. Even if you know, Poisson statistics rely on you assuming that there is a background population. But when you have a sample size of 1, that is very poorly constrained by orders of magnitude. And a lot of work that has been done in terms of predicting the number of Oumuamua-like objects we should see had not taken into account Poisson statistics and the uncertainties associated with the number of densities that is inferred from the detection of Oumuamua and from the detection volume of pan-stars and other surveys. And so I ran my own simulations and found that over the 10-year lifetime of LSST on the Vera Rubin Observatory, that somewhere between 0.4, we have a 95% confidence in there being somewhere between 0.4 and 84 Oumuamua-like interstellar objects discovered. So that is a very wide range, and you know, yes, it is possible that we might not find any Oumuamua-like object. It's very improbable, but it certainly is possible. And so we also did this as a function of size, because smaller objects tend to be more abundant. For example, we were talking about IM1 and IM2, those are meter scale objects. Oumuamua was a 100-meter scale object, and if you looked at for abundances, those of meter scale objects are way higher than those of 100-meter scale. It's the same in our solar system, same anywhere. And as a result, you could imagine looking for objects that are maybe a few times smaller than Oumuamua. Those should be more abundant, and because they're more abundant, there's a higher chance that, one, you'll discover them, but two, you'll find one with the right delta V, that fits within the budget of your rocket. And so we calibrated those across a variety of size distributions as a function of size. And so what we ended up finding is that if you have a mission with a delta V budget of 30 kilometers per second, very high, you'd have a good an 85% chance of finding a suitable Oumuamua-like object in 10 years. But you'd have an even better chance, greater than 90%, of finding an ISO if you focus on those that are a few times smaller in size. But then again, when you go down in size, you have less time to watch, because you detect it closer to its closest approach. So it's all about trade-offs.
Now, one last aspect of this to ask about is the idea of captured interstellar objects, where there might be captured objects of this nature sitting in various collection points in the solar system, presumably by Jupiter, that we could go look at that might be a lot easier. So is there any sort of plan within the Galileo project and this sort of thinking to go and look for those?
Yes. I'm actually engaged in work with Avi and some collaborators on, studying not just the theoretical parameters related to objects captured by the Jupiter subsystem, but by other such gravitational fishing nets in the solar system. And it is very hard to capture interstellar objects because they typically move very fast. And the ones that have a chance of being captured have to be moving, coincidentally, very slow relative to the solar system. And that vastly reduces the total abundance of objects that are even eligible to be captured. And then, of course, once you capture an object, it's a fairly unstable orbit that can then be perturbed. The object can leave the solar system. And so you also have to take into account the orbital lifetime. But then again, smaller objects are more abundant than larger ones. And if you're able to find, that's one way to boost your abundance. Then of course you have to focus on objects that will come closer to wherever your telescope is, whether it's on the Earth or in space. So that is something that we are actively studying, and LSST will certainly give us a better shot than Pan-STARRS.
Excellent. Thanks for the update, Amir. I hope you'll come back again once we get closer to expedition time to go and try and recover some of this stuff. But it's definitely one of the more interesting aspects of astronomy today, just the idea of being able to study in hand objects that could be from halfway across the galaxy for all we know.
I think so too, John. Thanks for having me.
Event Horizon and my channel are now available as a podcast on Apple Podcasts, Spotify, and YouTube memberships. Early ad-free episodes, bonus episodes, and sleep-focused content. Sign up now by clicking the links below to your platform of choice.
Well, the source of energy at the origin of life is the reaction between carbon dioxide and hydrogen. And amazingly, most of these reactions are exergonic, which is to say they release energy. If you have hydrogen and CO2, and you put them together in a Falcon tube and you warm it up to, say, 50 degrees centigrade and you put in a couple of catalysts and you shake it, nothing's going to happen. But thermodynamically, that is less stable. Two gases, hydrogen and CO2, is less stable than cells. What should happen is you get cells coming out. Why doesn't that happen is because of the kinetic barriers. It's because that's where you need the spark.
The following is a conversation with Nick Lane, a biochemist at University College London and author of some of my favorite books on biology, science, and life ever written, including his two most recent titled Transformer, The Deep Chemistry of Life and Death, and The Vital Question, Why is Life the Way It Is? This is the Lex Friedman Podcast.